Alright, so this video is going to serve as a bit of a recap. We're going to go through everything you need to know for DC circuits for level 3 and going through some of the key foundational concepts that you need to know from level 2 coming into level 3. Alright, so we can start off with a simple circuit, okay, like so. Where we would have a resistor right here and we're going to close the loop, okay? And this cell is going to have a 6 volt potential difference, okay? And so let's look at the energy transfer that's happening throughout this circuit. What this 6 volt is saying, if you haven't watched my what is voltage video, you can go check that out. But this is supplying 6 joules per coulomb of charge, okay? So every coulomb of charge is supplying 6 joules worth of energy, okay? And this is obviously 6 joules of electrical potential energy. And so we obviously know that this charge is going to flow throughout the circuit, okay? And right here we are following conventional current, right? So this is the positive terminal and this is the negative terminal, and we go from the positive and flow into the negative, okay? Again, as we know, conventional current is opposite to what happens in reality. In reality, we follow electron flow, and electron flow obviously comes from the negative terminal and goes to the positive terminal, okay? But like I said, in NCEA and also in higher level physics, it's convention to use conventional current. Now again, if you watch my video on what is voltage, we know that voltage is a mathematical difference between 2 points of a circuit. However, because in NCEA we deal with ideal wires, meaning the wires don't have any resistance, therefore the amount of energy that a charge will have at this point is the exact same amount of energy that a charge will have at this point. And so as we know, the potential energy between these 2 points is 0 volts, okay? And that would also be the case if we were to take the voltage from this point and this point, okay? The voltage between these 2 points is also 0 volts, okay? And that also leads me to another reminder. Voltage isn't just a value at a specific point. Voltage is a value from reference to one point to another, okay? So we can't just say, oh, what's the voltage at this point? That doesn't really make sense. We need to say, what is the voltage at this point with respect to another point? And so what is the voltage difference between these 2 points? Or we could say, what's the voltage difference between these 2 points, okay? Voltage requires 2 reference points in order for the value to make sense. Because again, it's the difference in energy per charge of 2 points within the circuit, okay? And obviously we know that the charges are going to flow through the circuit and therefore flow through our resistor. And as the charge flows through the resistor, we know that we're going to lose 6 joules of energy per coulomb of charge. And obviously, we can write this also as 6 volts. And because we start with 6 volts and we lose 6 volts as we go through the resistor, obviously at any point through this half of the circuit, we're going to measure 0 volts. However, if we were to measure the voltage at this point with respect to this point, let's say for example, this difference is negative 6 volts, okay? And if you remember from my what is voltage video, we know that the arrowhead always points to a potential rise. And so therefore we can say that this point is negative 6 volts higher than this point, okay? Which in other words, we can say it's 6 volts less, okay? So we can just as easily denote this as a arrow pointing this way and call this 6 volts, okay? All right, so the energy transfer process that's happening at this point is we know that our electrical potential energy is being transferred into heat / thermal energy, okay? Now, the only reason why it's being transferred into heat or thermal energy is because this is a resistor. Obviously, if it was another electrical component, it would be a different kind of energy. Let's say, for example, a light bulb, that would be transferred into light, okay? So essentially, the key idea is that electrical potential energy is transferred into another form of energy, which is more useful, let's say, for us, okay? Because that is the whole point of electrical circuits, is to be useful to humans. Okay, now let's sort of upgrade this circuit, if you will, and let's say we still have our 6 volt supply, okay, but in this time we have 2 resistors hooked up, okay, like so. Now again, this 6 volts just means that as charges flow through this power supply, they gain 6 joules of energy per coulomb of charge, okay? We should know that if we have components in series, the voltage is shared across those components. Now, although this statement is technically correct, I think this is the wrong way to look at it, okay? If you were to watch my videos on series circuits, you would know that components are in series if and only if there is one pathway for charge to flow, okay? So we can see right here that these components are in series because there's only one direction in which charge can flow, okay? There's only one pathway. Each component in this pathway resists charge to a certain extent, okay? And therefore the energy lost as charge flows through these components appears as a voltage drop, okay? And I'm just using V1 and V2 as arbitrary voltage values. And so therefore, as the total energy supply is fixed at 6 volts in our case, the voltage is shared amongst each component depending on how much each component resists current, okay? So it's not so much that voltage is shared across each component in series just because, it's a direct causation from the fact that charge can only flow in one direction in series, okay? So now to find the current within this circuit, let's add some resistance values. Let's say that this component is 3 ohms and this component is 5 ohms, okay? We should know that from Ohm's law, V is equal to IR, and therefore I is equal to V all over R, okay? We have our voltage given, okay? But what is our resistance? We should know that in series, resistance is the sum of all individual resistance values, okay? And so what that looks like in this case is our resistance total is equal to 3 ohms plus 5 ohms. And that obviously equals 8 ohms of resistance, okay? So in series, we simply just add up all the resistance values to get our total resistance, okay? Seems pretty simple enough. And if you don't know where that comes from, I'm pretty sure one of the first videos I made was deriving the 2 formulas for resistance, the one in series and also the one in parallel, so you can go check that out. I think it's in the scholarship physics playlist, so if you're looking for it, it's there. But also you can just scroll to the bottom of my videos and it will be there, okay? And so now we can calculate our current, where we have 6 volts all over 8 ohms of resistance, and we get a current value of 0.75 amps. There we go. Okay, so we get 0.75 amps, and like I said previously, because in series there's only one direction for charge to flow, our current value at every point in the circuit is equal to 0.75 amps, okay? No matter where we are in the circuit. Alright, like so. There we go. Okay? Now, what about calculating the voltage drop across each resistor, okay? Remember, like I said, both at the start of this video and also in my what is voltage video, I said that voltage is a mathematical difference, meaning if we were to take the voltage from this point and this point, we are therefore calculating the voltage across this resistor. And so how do we calculate that value? Well, again, we know that V is equal to IR. We know that the current going through this resistor is 0.75 amps because the current throughout all points in a series circuit is the same, okay? And we know our resistance value for the resistor is 3 ohms. And so we can just simply plug in our numbers and we get V is equal to 0.75 multiplied by 3, and we get a voltage value of 2.25 volts, okay? And so therefore, we have a drop of 2.25 volts across this resistor. Now notice the head of the arrow pointing to the point of higher potential. This just means that every coulomb of charge at this point right here has 2.25 joules more energy than this point right here, okay? And so there is a drop in voltage of 2.25, or you can say there is a drop of 2.25 joules per coulomb of charge, okay? Now we can also do the same for this 5 ohm resistor, and we get V is obviously still equal to IR, and we know our current is 0.75 multiplied by our resistance, which is 5, and that gives a value of 3.75 volts, and therefore we have a voltage drop of 3.75 volts. And again, we're taking the reference point from, let's say, this position right here and this position right here. And so every coulomb of charge from this position right here has 3.75 joules of energy more than this point right here. Now, there's also another way to calculate this value. We could have gone 6 minus 2.25, and that also would have equaled 3.75 volts, okay? How we got this is because we know that voltage is shared across all components in series, and because we have 6 volts in total, and we just found out the voltage of this, and there's only one more component, which is this component, we can therefore do 6 minus 2.25 and get the voltage across this component, okay? Okay, so that was when we added another component in series. How about when we add another component in parallel? Alright, so we will still have our 6 volt source. We would have our 5 ohm resistor, let's say, like so. Right now, we just have one component, and that is obviously the exact same scenario that we had over here. As charges flow through our power source, they obviously gain 6 volts or 6 joules per coulomb of charge, okay? And therefore, as there's only one component, there is obviously a 6 volt drop off at this point, okay? And again, because there's only one pathway for charge to flow throughout this circuit, the current at each point throughout the circuit is the exact same, and this current is going to be equal to the voltage, which is 6 volts, all over the resistance, which is 5 ohms, and so we get a current of 6 over 5 amps, okay? Now, when we add another component, let's say a 3 ohm resistor in parallel, what happens now? So, as you might have learned before, the voltage across parallel branches is the same, okay? You have probably learned that before. Now, what I'm willing to bet money on is that some of you don't actually know why that's the case, and again, that's not your fault, probably weren't even taught. But, like I said in my what is voltage video and many times throughout this video, voltage is a mathematical difference between 2 points on a circuit, okay? So we take the voltage at this point, okay, with reference to voltage at this point, we obviously know that the difference in voltage between these 2 points is 6 volts, just like the voltage between this point and this point is also 6 volts, okay? This is because we know the charge entering the power supply has 0 joules of energy, and as voltage is the amount of energy per coulomb of charge, if the charge entering this power supply has 0 joules of energy, therefore any voltage value measured between 2 points on this side of the circuit is going to be 0 volts, okay? And therefore as the charge gains 6 joules of energy as it goes through the power supply, that means from this point and this point, it's going to be 6 volts as we see up here, okay? Now what that means is, if the voltage across the power supply is 6 volts, because that is the voltage supplied by the power supply, and therefore the voltage between this point and this point is also 6 volts, and that also means the voltage between this point and this point is also 6 volts. What do you think the voltage between this point and this point is going to be? That's correct. It's also going to be 6 volts. And then what do you think the voltage between this point and this point is going to be? 6 volts. So the reason why voltage is split in components in series is because there's only one pathway, and therefore the energy of each charge must be shared. However, as this charge goes through this circuit, no energy has lost between this point and this point, and obviously this point and this point. And so each charge has the same amount of energy at this point as it does in this point, okay? So it hasn't lost any energy yet. And therefore, if this charge only goes through this component, then it must lose all of its energy, and so the potential will be 6 volts, okay? Now, moving on to calculating resistance in parallel. Resistance in parallel is given as 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and that continues on and on and on as you add more resistors, okay? And so therefore, in order to calculate our R total, we can take 1 over R1 plus 1 over R2 plus 1 over R3, and therefore if we have more resistance, we can calculate that, and we put it to the minus 1, okay? And so what that does is just take the reciprocal of that, and so you can do that in your calculator in the exam if you want. And to calculate our total resistance in our case, we have 1 over our first resistor, which is 5, plus 1 over our second resistor, which is 3, put it to the minus 1, and this gives a total resistance of 15 over 8, or we could say 1.875 ohms. There we go. Again, if you don't know where this equation comes from, again, it was in the same video where I derived the equation for resistance in series. Okay, it's that same video, one of my first videos. Now talking about current in parallel, if you remember, in series, current is the same because there's only one pathway for the charge to flow. Okay, however, we can see here that there are multiple pathways for charge to flow, and so it doesn't have to flow through one pathway. And so obviously this is held up by Ohm's law. If we use V is equal to IR, and therefore I is equal to V over R, we can calculate the current in each branch. As we can see, this branch has a total resistance of 5 ohms, and this branch has a total resistance of 3 ohms. And so let's call this branch 1, and this branch 2. Okay, so current in branch 1 is equal to the voltage all over the resistance of that branch, and we can see we only have a resistance of 5 ohms in this branch. If we had another resistor right here, let's say 4 ohms, then the total resistance of this branch would be 9 ohms, okay? But we do not have that, so let's erase that. There we go. And the voltage in this case is, as we discussed previously, is 6 volts. So we get 6 all over our 5, and therefore our current is 6 over 5 amps, okay? As for branch 2, again, V all over R, our resistance of branch 2 is just 3 ohms. Once again, if we were to add another resistor here, let's say again 4 ohms once more, the resistance on this branch would be 7 ohms instead, okay? But we only have 3 ohms, and so our voltage is once again 6 volts as we discussed previously, all over 3, and that gives a current of 2 amps. There we go. Now we can also calculate the total current of the circuit, And that is essentially the current right at this point, or the current right at this point, okay? It is the current before this division in branches, okay? And this current, we can either calculate it in two ways. We can again use our V is equal to IR, where our resistance is our total resistance, and this is our supply voltage, okay? And therefore we can get our total current is equal to the supply voltage all over the resistance total. And this gives 6 all over 15 over 8, and this gives a current value of 3.2 amps. Or, because we know that the current through here was 6 over 5 amps, or this can be written as 1.2 amps, and the current across here is 2 amps, this means that the current at this point is equal to 1.2 plus 2, which indeed is equal to 3.2 amps, okay? And as you can see, you get the same value, okay? Now, this is a direct causation of Kirchhoff's current law, which you will be learning about this year, or you probably have learned about it if you're watching this at the end of the year, okay? And so that is the recap of everything you need to know about DC circuits for level 3 NCEA electricity. All right, see you.